Before we pick up where we left off yesterday, let's just kind of go back over the statements that we went over. And if at any time we hit one and you're not sure about it, again, just pause the video and think about it, talk to the people at your table, and then pick up where you left off. So yesterday we looked at the PES data and we saw that it shows that our Bohr model is not supported for elements that have more electrons than beryllium, and which meant we needed a more complex model. The Bohr model was just too simple to show the interactions of the electrons in the atom. So this new, more complex model we call the quantum model. And while it does have a lot of mathematic equations associated with it, we're not going to look at those. We are just going to kind of focus on the concepts associated with this model. Okay, so we started out with the Bohr model, and the part of the Bohr model that we're going to kind of keep in this new model is his idea that the electrons can only be at certain places or certain energies in order to maintain their orbits and to continue around the nucleus without being pulled into the nucleus. Right. Then we brought in and talked about Heisenberg, who said that there is some level of uncertainty associated with knowing where an electron is and how fast it's moving. Like we cannot know completely everything about the electron, because the more we try to know one thing, like the location, then the less we know about the velocity, just because in order to measure something about the electron, we're kind of interfering with it with the way that we make these measurements because it's so small and our methods of observing it are very macroscopic, very large. And so we can't really observe it without interfering with its behavior. So the best we can do, according to Heisenberg, is to define a three-dimensional space where we are highly likely to find an electron. Okay, or excuse me, that was according to Schrodinger. And this space is what we were going to refer to as an orbital. So an orbital is a three-dimensional space where we are highly likely to find an electron. So think back to our analogy of the flies in the shed. Okay, so the orbital is kind of like the shed. It's our space, and we are highly likely to find the electron in that, but we don't know like the exact location of where it is within that. Okay, so again, this is Schrodinger brought together his Bohr's model with Heisenberg's uncertainty, and that bringing that together, we get this quantum model. And so the quantum model is going to give us information about the shapes and the sizes and the energies of these orbitals that the electrons exist in. Okay, again, it is mathematical, but we aren't going to be working with the mathematical part of it. We're just going to be working with the concepts, like the visualizations of the orbitals, that if we use the math and we graphed everything, we would get these shapes. So, okay, so these shapes are coming out of this mathematical model that we're talking about. Okay, so now this is where we are starting again. So this is the part where I want you to, again, as I read each statement, I want you to pause and I want you to think about it, talk about the statement with the people at your table. Make sure everyone understands or feels like they understand it enough to move to the next statement. Okay, so I'm going to read these one at a time. All right, as in the Bohr model, our quantum model organizes the area around the nucleus into energy levels, or sometimes they're referred to as shells. Each energy level is identified by what we call the first or the principal quantum number, which we use the designation N. And the energy level closest to the nucleus has the lowest energy electrons and is defined as N equals 1. Okay. Okay, now, if you are listening to me right now, that means that you talked with the people at your table and you understand the previous statement. Okay, if that's not true, you need to pause right now. All right. The energy of the electrons and the distance from the nucleus increases with the principal quantum number. As we move away from the nucleus, the difference in energy between adjacent energy levels decreases. Okay, so let's break that apart into those two sentences. So n equals 1 is the lowest energy electrons. N equals 2 is a little bit higher. N equals 3 is higher energy. N equals 4 is higher energy. And now we're talking about the energy of the electrons. All right. Now let me just pause a minute and differentiate. We are not talking about the energies that are on those PES data. Because remember, the energy on the PES data was the energy required to remove an electron from the atom. Okay, that's not the same as the energy of the electron. All right, so just let me clarify that. When I talk about the energy of an energy level, I'm talking about the energy of the electrons that are in orbitals that are on that energy level, which energy level specifies distance from the nucleus. So n equals 1, it's the closest in, and it's the lowest energy. N equals 2, a little bit farther out, and the electrons that are in N equals 2, or the second energy level, have a little bit higher energy. Now, the second statement, it talks about the fact that the energy differences are not linear. Okay, so even though N equals 1 to N equals 2, I have one numerical change in the energy level. All right, that doesn't correspond to the change in the actual energies of the electrons. Okay, N equals 1 to N equals 2 is a bigger difference in energy than N equals 2 to N equals 3 is. All right, and then likewise, N equals 3 to N equals 4 is an even smaller difference in energy. So let me see if I can do a little drawing, to kind of show you visually what I'm talking about. All right, let's just go back up here. All right, so say if I'm plotting, okay, my energy, all right, and so say this is N equals 1, all right, then say if N equals 2 is there to get the difference in energy, well, N equals 3 might be there, and then N equals 4 might be there. Okay, so that's what I'm saying. As we get further away from the nucleus, the energy difference between the energy levels gets smaller. Okay, now again, if you didn't pause, if you didn't understand the previous statement, then you need to stop, talk about it with your table people, and then move forward. Okay. An energy level can be divided into regions containing more than one orbital with the same energy and shape. So these regions within an energy level are called sublevels or subshells. Okay, so each energy level has within it separate like sublevels. All right, so it's divided into regions where we have orbitals that have the same energy and the same shape. And so kind of think about this. We're headed towards explaining, okay, why in our PES data did we have these peaks that maxed out at 2, and then we had some peaks that maxed out at 6. And remember, then we talked about like that one electron peak in scandium. We talked about how if we continued with it to where we maxed it out, that we would end up with a peak that had 10 electrons in it. Okay, so that's kind of what we're talking about within this. So the sublevels are a group of electrons that have the same energy and are traveling in paths that have the same shape to them. Okay, so now you should have that concept of, okay, I'm taking an energy level and I'm dividing it up into these sublevels where the electrons have the same energy and the same shape. All right, we identify these sublevels by what we call the second quantum number. All right, and these quantum numbers, these would be like variables in the mathematical equation that represents the quantum model. All right, so that's kind of what we're referring to. But again, we're only looking at them conceptually. So conceptually, this second quantum number, which they use with a cursive letter L, okay, it also has numerical values, but we typically in this course, we don't use the numerical values. We're not going to think about the numerical values. We're going to use the letter values that are assigned to that second quantum number. Okay, and so the ones we are going to work with are S, P, D, and F. Now, think about it back when we color coded the periodic table, right? How many different colors did we have on our periodic table? Well, we had 4, okay? Because we had on our PES data, we had 4 different peaks. When we thought about it, we said, okay, we see a peak that maxes at 2 electrons. We see a peak that maxes at 6 electrons, okay? We didn't go far enough to see the peak that would max at 10, but we talked about that scandium peak, that third type of peak would max at 10. And then we sort of addressed, those 2 little rows that are at the bottom of the periodic table and how they are 14 elements long. And so we said, yeah, well, if we went far enough and if everything matched the pattern perfectly, we would end up with a peak that had 14 electrons in it, that maxed at 14. Okay, so 4 different types of peaks. We got 4 second quantum numbers, S, P, D, and F. All right, and so if I'm going to identify a specific sublevel, right, I'm going to use the first quantum number that's going to tell me, okay, how far from the nucleus is this? What is its energy? And then the second quantum number is going to say, okay, what is the shape of this orbital? All right, now moving on. There are 2 more quantum numbers. All right, we're not going to deal with these in depth. All right, the first 2 quantum numbers are the ones we use the most in this course. All right, but the third and the fourth quantum number, I just want you to know that they exist. And I kind of want you to know conceptually, all right, why do we have 4 quantum numbers? Okay, so the third quantum number, which is called the magnetic quantum number, what that does is that identifies a specific orbital within a sublevel. So what we're going to see is that there are some types of orbitals, the P and the D and the F, that you can have more than one of those shaped orbitals in a sublevel. And so if I have more than one orbital that is that shape, I have to have a way of differentiating which one it is. And so that's what the third quantum number is for. Then the fourth quantum number, it's called the spin quantum number. And what we use that one for is that in a given orbital, I can have 2 electrons. And so I use that spin quantum number to specify, okay, which electron is that? Okay, sort of think about it like, okay, if I was going to like send a letter to an apartment where there were 2 people living in that apartment, all right, the fourth quantum number would be like the name of the person, all right? Everything else, first, second, third quantum number would get it to that apartment. But then that fourth quantum number would be my way of saying, okay, it's not that person living in the apartment, but it's this other person, okay? Okay, that being said, here's our next statement. To identify a specific electron, all 4 quantum numbers are required, okay? So the first quantum number gets me to how far from the nucleus is this electron. The second quantum number with that tells me, okay, in this energy level, what shape of orbital am I looking for? The third quantum number tells me, okay, if I have more than one of these shapes of orbitals, which one of those am I looking for? And the fourth quantum number tells me, all right, there are 2 electrons in this orbital. Which one am I talking about? And the name we give to that is Pauli exclusion principle. That says that I can't have 2 electrons in the same atom that have all 4 quantum numbers the same, okay? Because even 2 electrons, if they're in the same exact orbital, that last or the fourth quantum number is going to have to be different because that's the one that specifies which electron is it. Okay, so now the next couple of statements are just me kind of going back over this quantum number concept to kind of help you firm this up in your mind. All right, so if I have 2 electrons and they have the same first, second, and third quantum numbers, that means they are in the same orbital. They are moving in the same 3-dimensional area. All right, if I have 2 electrons and the first and second quantum numbers are the same, but the third and fourth might be different, then that means they're in the same energy level or sublevel, okay? So their orbital shapes and their energies are going to be the same, but they might not be in the same exact orbital. And then if 2 electrons have the same first quantum number, okay, it means they're in the same energy level, but the shape of the orbital that they are moving in might be different. It could be the same, but also it could be different because once we get past the first energy level, then all the later energy levels are going to have different shaped orbitals within them. All right. So now in this table, all right, what I'm doing is I'm kind of showing you the relationship between the orbital shapes and those peaks on the PES. So if we go, all right, so for this one here, this is our L was the second quantum number. That's the one that gives us our orbital shape. And also the different shapes also correlate to how many of those orbitals we have. All right. So the S orbitals, those are the peaks that only had 2 electrons. Okay. Those are the S type orbitals. All right. The peaks that maxed out at 6, okay, those are what we call our p-type orbitals. Now think about it. We had 2 electrons per orbital. So the S, the part you colored in on the periodic table that corresponded to the two electron peaks, right? It's only 2 elements wide, where each block on the periodic table represents an electron. Now, if we look at the part of the periodic table we colored to go along with the 6 electron peaks, right? It's 2, 4, 6, 6 electrons wide, all right? 2 electrons per orbital means 3 orbitals. And for that type of a sublevel, the P sublevel, right? We have 3 P-shaped orbitals. P, I think of peanut, like they look kind of like peanuts. Some people say dumbbells. I like to go with the shape that matches the letter. Okay, so P. So you have P-type orbitals. You get a P. They're all 3 the same, but you've got them oriented on the x-axis, the y-axis, and the z-axis. So that's why we can have 3 of those P-shaped orbitals, peanut-shaped orbitals. All right, and then the D, all right, we didn't, in our PES data, we didn't see them go this far, but, right, we had a taller peak. That peak would max out at 10, and those are these D orbitals. And so I think about D would be like D for double peanut, right? Because we got two peanuts to combine together to make our D orbitals, okay? And then we got the one that's kind of the oddball, and sticking with the D, I think donut, D, it's a donut peanut orbital shape. There you go. Okay. Now, then, all right, we definitely didn't get into these, but and because there's such variations from the pattern in these higher electron elements where it drops into those lower 2 rows on the periodic table. Okay, we're really not going to work very much with these at all. But if you look on page 297 of your textbook, you'll be able to see what those orbitals look like. See how they have like multiple lobes to them. So I kind of think, again, going with the F, they are F orbitals. So I think like flowers, okay? They're flower-shaped orbitals because they have lots and lots of petals springing out from the middle of them, okay? Again, for those F shape, right? If it's an F sublevel, then it's going to have 7 different types of orbitals, 7 different F orbitals within an F sublevel. Okay, and if we had, again, if we were seeing a PES on that, right, then we would have a 14 electron peak on the PES for that one. All right, but again, just because they deviate, there's so many exceptions to the rule when you get into those Fs. We're really not going to deal with those Fs. Okay. All right, so I'm going to start into or just talk through these later notes, but there's another video, and we're going to break apart this next part into Friday's discussion. Okay. But if you want to kind of tie everything together, then this will kind of segue you into that next video, and I'll put that link for that video. It's on there. I think it's in day 4 is the link to doing these electron configurations and orbital notations. Okay. All right, so our next topic where we're moving into is now we got to take this quantum model with these quantum numbers, and we're going to look at, okay, how do we describe or map the electrons in an atom? And the first thing we want to look at is that there are kind of 2 rules or principles that guide how electrons are going into those orbitals around an atom. And so the first one, it's called the Aufbau principle. And I kind of think of it as like, okay, this is the electrons are lazy principle. All right, the electrons are going to go into the lowest energy level that they can, until it's full, and then they have to move out to the next one. All right. So that's kind of what the Aufbau principle says. It's going to start into the lowest energy level and work its way out. Then the next thing is called the Hund's rule. And in the Hund's rule, it says that in those sublevels, so the P's, the G's, and the F's, where we have more than one orbital of that same shape, same energy, when those electrons go into those orbitals, they will go, if there's an empty orbital available, it's going to go there before it doubles up and becomes the second electron in an orbital. Kind of think of it like, okay, so say you had uh, three siblings and you guys lived in a 4-bedroom house, all right? So your parents get the one room, and then if there's 3 rooms remaining, right, each of you is going to want your own room, okay? Then if you get another kid coming in, right, that's when somebody's got to double up, okay? So electrons are kind of the same way. It takes less energy to put an electron in an empty orbital than it does to add an electron into an orbital that already has an electron in it. Okay, so and it's going to do, nature likes low energy, so that low energy is going to dictate that we're going to fill empty orbitals first and then we'll double up. Okay, this will become important when we're doing our orbital notation drawings on there. All right, so again, here I'm just going to show you what the 2 methods of describing how electrons fill the orbitals are. But to really see me work these out and give you some examples, I've already got another video where I kind of step you through that. So this is just going to be like the intro to show you what's coming up on Friday. So we have 2 ways. We got orbital notations and we got electron configurations. And so an orbital notation, we are basically mapping every single electron in the atom. And we do that, we use either a line or a box to represent the orbital, and then we use arrows to represent each electron. Okay, so you can kind of see here, and underneath the box or the line, we give the sublevel designation. Okay, and again, I'm not going to go into deep detail here. I already have another video that will show you how to draw these and explain it in greater detail. I'm just showing you there's going to be 2 ways that we are going to show how electrons fill the atoms. All right, so orbital notation. Key thing here is we are mapping every single electron. The other way that we do it is called electron configurations. And I think of these as like a summary of the sublevels. with an electron configuration, we're not mapping every electron. We're just kind of saying, okay, these are the sublevels that have electrons in them, and then we're using a superscript to say how many electrons are in a given sublevel. And if you remember from before, to define a sublevel, I need the first quantum number to tell me the energy level, how far it is from the nucleus. And then I need the second quantum number, the S, P, D, or F, to tell me what type of orbital am I dealing with. All right. And so that's what electron configurations, as you can see from our little diagram here, is that they just have first and second quantum number and a superscript for how many electrons are in that sublevel. Okay, so that gets you through today, and then we'll move on to the details of orbital notation and electron configurations on Friday when I'm back. But again, there is a video of me doing this in detail. It's on day 4 in the Unit 9 Evernote.